Hello everyone, good day to all. At the end of this class, do give a thumbs up, subscribe to my channel, click on the bell icon to get an instant indication for all new postings and leave a comment. Hi everyone, in this presentation I'm going to take you through solutions of unsolved problems based on Simpson's rules from exercise 17 in Capt Subramaniam's textbook volume 2 on ship stability. So as you can see on the left hand side, I have highlighted problem number 1. Given the following information, find the volume of displacement and the approximate mean TPC between the drafts of 8 and 9 meters. And the data given is for the draft 7, 8 and 9 meters water plane area being 2240, 2295 and 2355 square meters. So let's see how we can work this out. Here we have the data given to us in the problem. Drafts 7, 8 and 9 meters, the ordinates being 2240, 2295 and 2355 square meters respectively. 3 ordinates are given and the distance between each of the ordinates is 1 meter. So I'm going to use Simpson's third rule to solve this problem. The 3 ordinates I have labeled as A, B and C. At draft 9 meters, 8 meters and 7 meters respectively. The respective water plane areas are mentioned here. And the Simpson's multipliers for the third rule are 5, 8 and minus 1. So when we multiply the water plane area with the Simpson's multiplier, we get the product. And as you can see, the sum of the products finally adds up to 27,895. Therefore, water plane area, as per Simpson's third rule, works out to 1 upon 12 into h into the sum of the products. And when we substitute all the values, we get the water plane area equal to 2324.583 square meters. Now we know the formula for TPC is water plane area divided by 100 into the relative density of salt water. Therefore, when we substitute the values of WPA, water plane area, and we know the relative density of salt water is 1.025, we get the approximate mean TPC between the drafts of 8 and 9 meters is equal to 23.827 metric tons per centimeter. Moving on to problem number 2. Find the volume of the lower hold 20 meters long whose transverse cross-sectional areas at equal intervals from forward are 120, 116, 101 and 80 square meters. The information given to us in the problem is here. Length of the hole equal to 20. 4 ordinates are given, 120, 116, 101 and 80. Therefore, the total number of sections are 4 minus 1 equal to 3. And the distance between each of the sections, intersection point, is 20 divided by 3 meters, which if you work it out, works out to 6.667 meters. So I'm going to use second rule to solve this problem. I've given the ordinates A, B, C and D. Their areas are mentioned over here. The Simpson's multipliers that I'm going to use are 1, 3, 3 and 1. And when we multiply the areas with the Simpson's multipliers, we get the products. Thus we have the 4 products and the sum of all these four products is equal to 851. Therefore, volume of the hold is equal to, using Simpson's second rule, 3 upon 8 into H into the sum of the products. And when we substitute the values, for H is equal to 20 divided by 3 and the sum of the products is equal to 851, we see we have a 3 in the numerator and a 3 in the denominator, which I have cancelled out. Thus, it works out to 20 divided by 8 into 851, and that gives me an answer of 2127.5 cubic meters. Problem number 3. Find the displacement at 5-meter draft in salt water if the water plane area in square meters is as per this table that is given over here. So here I have the data taken from the problem, and I'm going to use Simpson's first and second rules to get the answer. The drafts from 6 meters to 0 meters is under this column. Since we have full breadths, the ordinates are as per this problem. The Simpson's multipliers that I'm going to use for the drafts 5, 4 and 3 meters are 1, 4 and 1. And therefore, when we multiply the ordinates with the Simpson's multipliers, we get the product. And I'm going to add this. The sum of these three products is equal to 11,270. Thus, the underwater volume works out to 1 upon 3 into H into the sum of the products. And when we substitute the values, we get the underwater volume is equal to 3756.7 cubic meters, which I'm going to term as A. Using second rule, I'm going to use for the drafts 3 meters, 2 meters, 1 meter and 0. And the Simpson's multipliers that will be used are 1, 3, 3 and 1. Ordinates multiplied by the Simpson's multipliers gives you the product, and therefore the sum of these four products is 9020. Underwater volume basis Simpson's second rule is equal to 3 upon 8 into H into the sum of products, and when we substitute the values, we get it equal to 3382.5 cubic meters, which I'm going to call B. Thus, the total volume from 5 meters down to 0 meters is equal to A plus B. And that gives me a total of 7139.2 cubic meters. And we know displacement is equal to underwater volume multiplied by the relative density of the water in which the ship is floating. And in this case, it is salt water. Therefore, we multiply the underwater volume by 1.025 to get an answer of displacement equal to 7317.7 metric tons. Now, the same problem can also be solved using Simpson's rules 1 and 3. Using Simpson's rules 1, I'm going to use the ordinates, the Simpson's multipliers 1, 4, 2, 4, 2, 4, 1, and adding up all the sum of all the products is equal to 27,810. Therefore, the underwater volume basis Simpson's first rule is 1 upon 3 into H into the sum of the products, and when we substitute the values for H and the sum of products, we get that equal to 9270.0 cubic meters, and that I'm going to call A. Now the thing is, the displacement wanted is at 5 meter draft. So basically now we have to find the displacement that would be from 5 meters to 6 meters and subtract that from what we have found using Simpson's first rule. I'm going to calculate the underwater volume between 5-meter draft and 6-meter draft and subtract that from the underwater volume from 6 meters down to 0 meters, which is the point A. The Simpson's multipliers used are 5, 8 and minus 1. And when we add, we get the sum of the products is equal to 26,910. Therefore, underwater volume between the drafts of 5 and 6 meters is equal to 1 upon 12 into H into the sum of products. And when we substitute the values for H and the sum of products, we get that equal to 2242.5 cubic meters, which I'm going to call B. Therefore, the underwater volume from 0 meters to 5 meters will be equal to A minus B, as I have written over here. And when I substitute the values for A and B, I get the underwater volume at the 5-meter draft is equal to 7027.5 cubic meters. Displacement is equal to underwater volume multiplied by the relative density of the water in which the ship is floating, and in this case it is salt water. Therefore, the displacement is equal to 7027.5 multiplied by 1.025, giving me an answer of 7203.2 metric tons. There is a third way of solving the same problem. Once again, I'm going to use Simpson's rules 1 and 3. In the first step, I'm going to calculate the underwater volume until the 4-meter draft. And then in the second step, I'm going to calculate the underwater volume between the 4 and the 5-meter drafts. And when I add the two, I'm going to get the underwater volume at the 5-meter draft. As you can see, the sum of products is equal to 15,300. That is between the drafts, that is until the 4-meter draft. And therefore, the underwater volume is equal to 1 upon 3 into H into the sum of products. That gives me an answer of 5,100 cubic meters, which I'm going to call A. And I'm going to find the underwater volume between 4-meter draft and the 5-meter draft using the Simpson's third rule. The Simpson's multipliers used in this case will be 5, 8 and minus 1. As you can see, 2010 into 5 is equal to 10,050. 1920 into 8 is equal to 15,360. And 1,580 multiplied by minus 1 is equal to minus 1580. And when I add up these three, I get the sum of the products to be equal to 23,830. Therefore, the underwater volume using Simpson's third rule will be 1 upon 12 into H into the sum of products. And when I substitute the values for H and the sum of products, I get that equal to 1985.8 cubic meters, which I'm going to call B. Now, adding the two, A and B, I will get the underwater volume until the 5-meter draft, which works out to 7,085.8 cubic meters. And displacement is equal to underwater volume multiplied by the relative density of the water in which the ship is floating, thus giving me a displacement of 7,262.9 metric tons. Now you will wonder which of the three answers is correct. In the first instance, it was 7,317.7 metric tons. Second instance, 7,203.2 metric tons. And in the third instance, it was 7,262.9 metric tons. Don't worry about this. This is just for academic value, for just to solve the problems. If you use any of the methods that I have shown over here, your answers will be marked correct. Problem number 4. Find the quantity of the coal at storage factor 4 cubic meters per metric ton that a coal bunker can hold if its cross-sectional areas at 5 meter intervals are 9, 11.3, 12.6, 12.4 and 11.2 square meters. So the 5 ordinates, I have labeled them as A, B, C, D and E, and I'm going to multiply them with the Simpson's multipliers. Excuse me, it's just a minute. Let me just correct it. Thereby getting 5 products, and the sum of these products is equal to 140.2. Thus the volume of the coal bunker is equal to 1 upon 3 into H into the sum of the products is equal to, when we substitute the value for H, which is 5, and the sum of products is equal to 140.2, we get that volume is equal to 233.667 cubic meters. Storage factor given to us is 4 cubic meters per metric ton. Volume of the coal bunker we just found out is equal to 233.667 cubic meters. Therefore, the quantity of coal loaded will be equal to volume divided by storage factor, thus giving us an answer equal to 58.42 metric tons. Coming on to the last problem in this exercise, problem number 5. We have to find the displacement and TPC at the 6 meter draft in fresh water this time. And given are the water plane areas for the drafts from 6 meters down to 0 meters. The values given in the problem are these. 7 ordinates are given. H is equal to 1. So I am going to use Simpson's first rule. Against the draft, I have got the ordinates, the Simpson's multipliers and the product. When I add up all the products, the sum of the products is equal to 105,911. And thus the underwater volume is equal to 1 upon 3 into H into the sum of products. And when I substitute the values for H and sum of products, I get the underwater volume is equal to 35,303.7 cubic meters. Displacement is equal to underwater volume into the relative density of the water in which the ship is floating. This time the ship is floating in fresh water, and we know that the relative density of fresh water is 1, unity. Therefore, the displacement works out to 35,303.7 metric tons. And TPC in fresh water is equal to water plane area divided by 100 into the relative density of fresh water, thus giving us 5855 divided by 100 into 1 equal to 58.55 metric tons. And 5855 is the water plane area at the 6 meter draft, which is where we want the TPC to be calculated. At the end of this presentation, do not forget to give a thumbs up, subscribe to my channel, click on the bell icon to get an instant indication of any new video that I post and to leave a comment. Thank you very much.